One more try with Zoom.
Now it's streaming live on YouTube, it says.
It does. It doesn't
Yes.
say, it doesn't say to me.
It says it here, yeah.
Okay. Meeting is, let me check on YouTube just to make sure. Okay, everything looks good. Okay. Let's start then. Welcome everybody to the Monsoon Geo Seminar. This week we will have Christian Betzler from University of Hamburg talk about Monsoon. And Christian has come to this topic via IODP in a wonderful expedition, 359 in the Maldives archipelago. He's a specialist in carbonate platform evolution, one of the foremost specialists in the world, but has reached being with the evolution of the Maldives being so tied to the monsoon. He has entered that field with extremely interesting results in the last couple of years published, and I'm looking forward to see what new things have come up from that expedition. He has done his PhD at the University of Tübingen with a stint for habilitation in Frankfurt, and then a joint appointment at the University of Hamburg and Cambridge, and has been at the University of Hamburg for a long time now, dealing with interest mostly in carbonate platform evolution, as I said, with research cruises all over the world. And of course, at classic places like Bahamas, Maldives, and Mascarene Plateau. Welcome to the Monsoon Geo Seminar. And Christian, please take over.
Thanks, Livio. I will try to share my screen. And you tell me if it works.
Yeah, we had some small problems before, but it works perfectly now.
Works perfectly. This is good because it did not work on the weekend. So, well, technology, that's the future.
Okay.
Thank you for the kind words. I mean, as you told, I'm a carbonate sedimentologist, and I'm usually working in shallow water deposits. And we had this wonderful expedition to the Maldives where Livio, in fact, should have joined, but there were some questions about permits in waters off the Maldives, and he could not join finally because his topic could not come in during the cruise. And so as a carbonate sedimentologist, it was fascinating for me to learn that such carbonate platforms would also record the paleoceanographic signals linked to the monsoon. So what I will try to show you is what record we do have in the Maldives, mainly based on IODP expedition 359. I also have to acknowledge the funding by the Deutsche Forschungsgemeinschaft, the German Science Foundation, the Ministry for Education and Research, and for sure IODP and ECHO to make it possible that we can do this wonderful science. And thanks also to Livio, to Peter, to Tara, to all the organizers of this fantastic webinar, where you can really learn a lot of monsoonal questions. So the topics I would like to discuss with you today are two topics. So I will try to take you out there to see how circulation changes during the Miocene onwards affected the Maldives carbonate platform. So how the modern Indian Ocean circulation pattern started around 13 million years ago. We will also have a look at some data which show that the speed, the intensity of these currents change through time. Then in the second block, thematic block, I would like to show you the record we think we have on the dust flux to the Maldives, which started around 20 million years ago. We can see how the dust flux increased between 13 and 8 billion years, and we can reconstruct the wind intensity, the dust flux, in a higher resolution during the last 4 million years. So I will not discuss about riverine input or hinterland input or mountain building processes, because we are sitting in the middle of the Indian Ocean in the isolated carbonate platform, where we get these open ocean signals in there. So I have 3 blocks for my talk, and the first block is to introduce you to the present day conditions. Everybody is a specialist here, so everybody knows how the monsoon works. But I think some words, some presentation should be done how this can be recorded or how this affects the Maldives depositional system. So if we take a look at the present day conditions, for sure, there we have these reversing monsoonal wind systems. On the left-hand side, the winter monsoon. On the right-hand side, the summer monsoon in the Maldives are sitting here somewhere where my red laser pointer is now. And this means that over the year, we have a seasonal, almost full reversal of the main wind directions. The length of the arrows gives the speed of the wind, and we all know that the summer monsoon winds in this area are stronger than the winter monsoon winds. This reversing wind pattern affects the surface circulation in the ocean. What you do see here on the right-hand side are 2 maps for the velocity measured at the ocean surface, for the winter monsoon in the upper map and for the summer monsoon in the lower map. There are these little arrows in there. The little arrows give you the speed of the current, and the red, the hot colors, give you the areas where we have the highest current speed, and the location of the Maldives is indicated by this little white rectangle in there. And for sure, the Maldives are really in this area where you have this seasonal 100-degree reversal of currents. How do these currents affect the system? There are several signatures in there, several processes. One important process, is that we have this topographically controlled upwelling. What you do see here is remote sensing data showing the chlorophyll alpha concentration for January on the left-hand side and for July on the right-hand side. So the warm colors, the hot colors again, are high chlorophyll alpha concentration. This means that we have a high primary productivity in there. And what is nicely shown in here, during the winter, we have the flows coming from right to left, and the water is pressed through this wall, this topographic wall of the Maldives. And when it flows, when the water flows through there, in the wake of the platform, in the down current side of the platform, you get this upwelling system, and this upwelling system almost reverses during summertime. Just as an interesting side note, this is very well noted by the organisms. Here you see an image of manta, or Mobula alfredi, how it's called today. And on the left-hand side, you see the occurrence of this manta throughout the year. The northeast monsoon in here, the southwest monsoon in here, and the black dots are the visual observations of manta. This is relatively interesting because manta feeds on phytoplankton. So these big fishes, they follow seasonally, they follow these upwelling cells and go there in the areas where you have the highest nutrient influx. And this is shown in the 3 graphs in here, where you have the wind pattern, the chlorophyll alpha, and the manta occurrence. And what we very nicely see, that the summer monsoon episode is much stronger and of a longer duration than the winter monsoon episode, but the mantas really follow this upwelling cells. So that's pretty clear what happens at the surface. Let's take a look now how this affects deeper water masses. What you do see here are ADCP data, which are acoustic Doppler profiling data, shipboard measurement. So you send sound waves through the water, and the sound waves are reflected. It's a very high frequency signal, and they are reflected as small particles swimming in the water. And if these particles move, you have the Doppler effect, and this can be recorded here in the ship. And what you do see here is a cross section to the Maldives. So that's the seafloor of the Maldives in white in here, and you see that the ADCP data cannot fully look at the seafloor because there are these side lobe interferences. So you have interference signals near the sediment surface for several tens of meters. So you don't really see what happens at the sediment surface. You only see what happens in the upper water column. And this upper graph in here has a scale from these hot colors, which are high current speed, so a meter per second. This red color and the blue colors are slow current speed, and you really see the upper 200 meters. The current flows in here from almost east to in this east to west section with a relatively high velocity, and how it is expected with further in deeper water masses, you have a slowdown of the current, with one exception. If you take a look here on the left-hand side, you have an area, you have this wedge of higher current speeds again near the seafloor. And the explanation for this is shown in this lower graph. In this lower graph, now the colors give you the direction of current flow. So the green colors mean that the current is directed toward the south, and the red colors indicate that the current is flowing to the north. So what we do see here is this water mass where we have these reddish colors, and then here in the area where above we have this higher current speed, you have these reverse currents again. This is an upwelling cell or near the seafloor. So a very complicated current pattern, which here we only have the image for the winter monsoon. That was our ship availability. We don't have the data for the summer monsoon, but we can imagine that the system just reverses. And this reversing system has its signature in the sediment structure at the seafloor. What you do see here, this is a publication which was just submitted by Thomas Littmann. What you do see here are multi-beam data. The left-hand side are multi-beam data shown with a dip angle of the seafloor feature. So these blue colors is a relatively flat surface. These hotter colors are relatively steep angles. And we have this for the western edge of the platform, for the eastern edge of the platform. And you see, you can see in here already that at each of the passages connecting the this inner sea with the open Indian Ocean, you have this submarine sediment waves moving in here, which shows that the currents are strong enough to move sediment in there and accumulate it here in the center part of the platform. Here the depth data to this, we are in water depths of 400 to, let's say, 600 or 500 meters of water depths, and very nicely shown also these submarine dune fields. And by using the direction of the dunes and the orientation of the dunes, we can show that on the eastern side of the platform, the dunes migrate towards the interior of the platform, and the same applies on the western side, where they just also migrate here towards the east. So the numbers in here behind these arrows, these numbers are just the numbers giving the speed, the calculated speed of the bottom current. You can calculate this by using the form, the size of the submarine dunes. So this is important because nowadays, also we are in a water depth of several hundreds of meters. We see how these water masses move and accumulate sediment here in this area. The Maldives are also still in the range of the Indian Ocean oxygen minimum zone. Here you see west to east cross section from the Oman margin over here to the Chagos-Lagadiv Ridge. This is the area where the Maldives sit in there, and we can see that there's a tongue of oxygen minimum waters reaching over to this area. And we will try to trace this also in the geological record. Finally, this is a very nice study done by Teresa Kukelova in Edinburgh with Dick Kroon. They worked a lot on the dust and aerosol input to the Maldives. I will show more detailed data later. What is important is that here you have these 4 remote sensing images, February and April up here, August and November down here. And we can see that during the winter times, the Maldives are still in the reach of these dust plumes coming down here south from the Indian subcontinent and further to the west from the Arabian Peninsula. So these are all processes we can trace back in time, or we will try to trace back in time. What's the advantage of the Maldives? If you look at the sediment thickness map of the Indian Ocean, for sure the sediment thickness is highest around the continental margins, with the highest values here in the Ganges-Brahmaputra fan and delta system, and in the Indus fan system. And the Maldives are here sitting in here in the middle of the ocean. They have a relatively thick succession of sediments, which is really isolated from this terrestrial influx, or mostly isolated from this terrestrial influx. So the Arabian Sea paleo-oceanography, we were not the first to describe this. Many years ago, there were a lot of studies linked to ODP Lake 117, where they looked at the upwelling system in front of Oman with several drill holes. There's a nice recent compilation by Gupta and co-authors in the year 2015 who discussed this data in detail. The first to describe how the paleo-oceanography in this area is linked to the wind system was Dick Kroon in the early 90s, where he noticed by tracing the occurrence of planktonic forams indicative of high nutrient contents, that this upwelling system must have started around 8 million years ago, and for sure it's a wind-driven upwelling system there. Gupta expanded this data in a very detailed paper. I had to separate the graphs side by side. So what you do see here are the added data regarding the organic content of the sediment of several ODP sites, and they traced a little bit back the onset of these wind-driven upwelling by looking at the organic content of the sediment, and they traced it back to around 12.9 million years. But it has to be said that Dick Kroon already at the time being, he also noticed some earlier peak of this Bulloides, Rubigarinus bulloides in this succession. Just recently, a nice paper by Orbialik and co-authors revisited these sites and came to quite similar results. So they can trace the primary productivity also by looking at the diatom occurrence. And again, the diatoms, they begin to be more abundant, so at around 12 million of years. But if you go back in time, you see that there are some peaks a little bit earlier, around 13.5, 14 million of years. And they can also, by tracing the manganese content of the sediment, they can trace back anoxic conditions at the seafloor back to almost 14 to 14.5 million of years. So this is the frame. This is what is known. And let's look how the Maldives data fit in there. So the Maldives is a carbonate platform, and it's in fact it's a giant natural sediment trap. Here you see a seafloor map of the Indian Ocean. So the southern tip of India, Karlsberg Ridge, and here the Chagos-Lagadiv Ridge with the platform sitting in there. And this white line in here gives you a cross section through this platform, and you can see that this cross section shows that this Maldives is like a wall sitting in the, it's like a wall sitting raised about several thousands of meters above the surrounding Indian Ocean seafloor. But it's not a closed wall, it's an open wall, so the water can flow through. And you see that we have these elevated edges here, the elevated shoulders of the platform, and we have this depression in the middle here. So this is our natural sediment trap. This is our inner sea, where all the material which has been moved by currents from the sides in there finally are deposited. Just to show you the current regime in the area, so that image is not very of high quality. That's a very nice study of Owen et al. They looked at the possibilities of producing current by using the hydrodynamic energy in there. So they did a lot of modeling. So what you do see here is the Maldives archipelago, and that's a little bit bigger. So showing how the winter flow and the summer flow is pressed through these passages into this inner sea natural sediment trap. And if you look in here, you can see that the current speed is high and elevated in the passages between atolls. We've seen the seafloor structures before, but then they relax in the platform interior, and that's the area where we can reconstruct this fluctuation in the monsoonal regime best. Okay, so now let's look at the long-term evolution of the Maldives archipelago. So the long-term evolution means that now we are taking a look. We are trying to take a look at how the onset of the circulation affected this carbonate platform. And these are not only data produced during IODP expedition 359. There has been several industrial data and industrial wells in the area. One well was situated in here in one of the still active atolls, and it reached basement, which is a volcanic basement. The other well was located here in the inner sea in our sediment trap. It also reached basement, and both of them came up with an age of the volcanics of around 50 million of years. So what we do have here is a 3 kilometer thick carbonate platform, which grew through during the last 50 million of years. Here the position, the projected position of our ODP cores in this area. So that's a synthesized cross section projecting several view planes together. So this volcanic basement is dissected by a system of half grabens. In the interior of the half graben, this has not been really drilled, but it is supposed that there is a lacustrine succession in there. And then on the shoulders of these half grabens, this shallow carbonate platform, so large benthic forams, corals, red algae grew and formed this carbonate platform, which has a complicated story. So you see that it grew, then at a certain moment it shrunk in space, then the platform width again grew at some time, and then there was a major change. This yellowish color indicates the onset of drift deposition. That is the onset of these current controlled deposits. And together with these current controlled deposits, with the occurrence of these current controlled deposits, parts of the platform were drowned, what we call the shallow water. The shallow water carbonate production was turned down, and in other areas the shallow water carbonate production still worked on, and this forms the fundament of the atolls which are still active today. And we have this huge series of drift deposits sitting in here. So we can separate the platform story in two major episodes, and this separation, this break in platform evolution, is very nicely imaged also in seafloor data. Again, the multi-beam data here. So what you do see here, this little small map, that's a merged satellite imagery with our multi-beam data, and the little white rectangle in here give you this more detailed view. Be careful here, the north arrow is down towards the right, so north is towards the right down there, and we see a very nice succession of different carbonate platform types. So we see that here we have this kind of drowned barrier reef. So you can imagine this like a very huge platform with a reef rim in here and huge reef flats, and at some time this barrier reefs, this latest episode of barrier reefs, drowned, and we have this let's say this remaining little platforms, little atolls, which are here, which were still active during a certain time before also drowning. Here again, you see these very nice submarine dunes in here. And so these now drowned atolls, these two are not very well preserved, so that's more mound shaped. That's a different story. But let's take a look at this one at 450 meters of water depth, because if we look carefully at this structure, we see that this structure is very similar. The geometry of this teardrop-shaped atoll is very similar to the recent atoll. And here it's a whirlwind image of a atoll just some kilometers away from this drowned atoll, which is now in more than 400 meters of water depth. And what you can see here, that in both cases we have this current action shaping this teardrop form. This means that when this barrier reef drowned, there was a demise of this barrier reef, this kind of current controlled atolls switched in. So this is the time where we think that this monsoon circulation system in the Maldives started. But I will show you more data to this now based on the ODP, on the IODP wells and cores. So what you do see here is the map of the area we visited. Here again, just an overview, a Google overview of the Maldives. So a double row of atolls. This inner sea in here. The inner sea is connected to the open Indian Ocean by these passages here, which allow the circulation to come in and to come out. And this stippled white line gives you the area shown in detail in here. So we drilled two what we call transects, so two rows of sites, one here to the north, one here to the south. And then we also drilled one site in here in an area where we have where our seismic data and our multi-beam data showed us that there was no high current speed to be expected there, so no much reworking to be expected there. So a high energetic area in here to the left, and more protected area here to the right. And here ODP leg 115 site 716 was drilled earlier. I will also show some data on this one. So just the H depth plot for these drill holes. You see that we drilled we caught one site with a length of a little bit more than 1 kilometer, and the oldest deposits we touched were late Oligocene in age. It's a little bit difficult to say to precisely say what late Oligocene this is, because these are very recrystallized and very cemented rocks, and there are no planktonic forams or calcareous nanoplankton in there. There are large benthic forams which tell us it's a late Oligocene age, but it's not possible to pinpoint this a little bit more. So we have a good age control in here, and what you also see here, these vertical lines, these are just the unconformities as defined in the seismic profiles. And we have 11 unconformities here in the older part. And then comes the drowning unconformity, which is this DS1, and then several sequence boundaries here for this drift and current control part. So if we go into the one of the seismic lines, which is a reference line here, again a west to east line through the Maldives platform, as you can see, we can only image the upper part of the succession, so we don't reach the acoustic basement in here. It's too deep, and our seismic source and our streamer are not designed to go so far deep, but we can very nicely see how we have this platform growing in here. So we differentiated several steps of platform evolution. The most important step is step 5 in here, the turnover 5. There we lose this progradation. We have this drowning unconformity on top of it, and we have this huge drift deposits filling our sediment trap here in the interior of the inner sea. Here are some ages to these turnovers. That's a little bit shown more versus age in this graph, where we have this turnover. So these turnovers 1 to 5, these are turnovers which show us that we had sea level changes really dominating the platform evolution. So we can very nicely reconstruct the high stand and low stands like you would expect in a sequence stratigraphic textbook. We can really show how the unconformities are really related to sea level low stands. And then here with this step 5, this system gets lost, and currents dominate the system, and reworking of currents are the main factor controlling the sedimentary evolution. Let me take you through the succession, just to have to make a little bit more, not so theoretical, just some images to show the interesting stuff down there. So the most interesting stuff for several people is this part of the succession, which is the base of the succession almost. And I will concentrate only on this part of the transect, of the northern transect, where we have these 3 ODP sites. Here you have the ages on the right-hand side. We do have the sequence boundaries in here, which are dated. I showed you the ages before. And here, just about the Oligocene, Miocene boundary, around the boundary, we found this pitch dark and black deposits. These are subpropales, which have organic contents of up to 35%. That's quite a lot. The age is in here. They were formed between 21.5 to 24 million of years. And these subpropales and the white deposits in here between, in fact, are chalks. So here is a very nice study which just came out. Jeremy Young, who worked on these wonderfully preserved nanoplankton faunas. Here, just SEM images of these dark layers, and you see the preservation of them. Some of these plankton individuals of these coccoliths is just pristine. They are beautifully preserved, and they did a great work just looking at potential difference between these subpropale layers and the white layers, and we can see that there is almost no shift in the flora in there. So it is not a nutrient-induced signal we do have here, but it's probably a sea level signal. Here, a nice study done by Peter Swart in 2019. They did a geochemical analysis of these 2 layers, and they came up with a model where this anoxia formed during sea level low stand in our sediment trap. And then during high stands, our sediment traps is very well oxygenated, and you get these white chalks. Here are some values, and this curve to the right here is important. So that's the nitrogen isotope values, and you see they are always lighter than 3. This means that we really don't have input of upwelling waters in there. So it's a pure sea level dominated signal. We move a little bit up the succession, and there we have the platform on the left-hand side, and the slope and tour slope of the platform. And as one would expect, at the tour slope and slope of the platform, you get the input of reworked material. So you have these slumps and debris flows coming in there, and these alternate with this kind of very strongly bioturbated deposits, which we in counter sedimentology we call periplatform ooze. So that's export of fine-grained material from the platform interior mixed with pelagic components. Here it's a wacky stone already because it's well lithified. But beautiful, you see this beautiful bioturbation in there, which is very nice. Oh, I moved in the wrong direction. Excuse me. Now, let's take a look at the platform itself. So we drilled this one side U1465 because we needed to have a positive test that the seismic phases we do see here are really also related to different lithologies. And we drilled this side. We wanted to go deeper, but there is a lot of caving in there, a lot of solution going in there. So it was very difficult, and we only could go several meters in there, or several tens of meters, but we got the most important information of all. We got the information that we are really dealing with corallial reefs in there. So this, at the time of deposition, was really a shallow water reef. And on top of this shallow water reef, coming in here, you have this totally different seismic phases. You have the drowning unconformity, and what we do have are these very coarse-grained carbonate drift sands. You see all these sediment waves in there. You've seen the multi-beam imagery before. So very coarse sands, a mixture of shallow water components and pelagic components. And then we have this interesting sediment body here to the right, which has a lobe shape, and we call this a delta drift because we think that this is a drift body which really works like a subaquatic delta. And why we think that is shown in here in the reconstruction, reconstruction performed by Thomas Rittmann some years ago, where we can see for one of these sequence boundaries in here, we see that we have these channels in there, and in front of these channels, we have these channel mouth bars of carbonates deposited in the subaquatic environment. All this was covered by water, but you can really imagine how the water flows through there, and you have this deposition in there. These are the location of the coring sites. And because it's so beautiful, just a thickness map from the lowest sequence of these delta drift deposits, where you really nicely see these depot centers sitting at the mouth of these channels. So now one question remains is, why did this platform drown when the current came in? Anna Ling just presented, some weeks ago, presented a very nice paper where the phases evolution is linked again to the nitrogen isotope data for this time interval. And what you do see here are the nitrogen isotope data for two of the wells, U1468, U1466, with different colors. Here, this blue to yellow turnover, again, is the turnover from this sea level dominated to the current dominated system. And we can see that, yes, there are some little excursions and some little peaks of upwelling signatures, but the line is almost flat. So we think it's not so much the nutrient input which really deteriorated the reef growth in here, but it's really the hydrodynamic, the physical pressure of the currents on these reef system, which led to the demise of this system. We can see, interestingly, that during the last, let's say, 2 to 3 million of years, the upwelling system started to pick up a little bit, and we have this higher nitrogen isotope values in there. This is very nicely backed up by a study done by Jesus Reolit in 2020. He looked in detail at the phases of these relict platforms. In here, you see a little image of a seismic profile in here. We have the sea level control platform in here. We have one major unconformity in here, and this is one of these relict bodies here. You very nicely see the reef rim even in here. One current controlled platform which all already developed at the time of these monsoonal pressure on the Maldives, and here on top on the drifts. And what he did is a very detailed classical facies analysis. He looked at the components, and you very nicely can see that there is no floral or faunal change above or around these drowning unconformities. So it's not nutrient influx, but it's the influx of this current, the physical pressure of these currents acting on this platform, which led to the drowning. Here, that's a study which has just been submitted again by Thomas just some weeks ago. That's the same section you have seen already. So we have these drift deposits, and we can differentiate between different types of drifts. So delta drift, sheeted drift, elongated mounted drift. So a lot of terminology in there. The interesting part of it is that if we look now at these data, we see that we have sediment waves field in the interior of our huge sediment trap. And this means that here we had an episode where the current speed must have been more elevated. And the dating of this is between 10.5 and 5.5 million of years. So this is an interesting observation. We can see that the current system was not stable through time, but that it had phases of acceleration and of deceleration. So the last site I would like to present you is this protected site, this hydrodynamically protected site, U1467. The small little line here gives you a seismic profile through that. So it took us a long time to find a good place to call this site, because we wanted to avoid any sediment waves or any unconformities. And we finally found this beautiful succession where, at least at the seismic scale, we don't have any unconformity. You see, if you move a little bit more to the right, you already get the sediment waves. That's not the place you want to drill. You want to core in here where you have a supposedly continuous succession in these sheeted and mounted drifts. And what we found here is just a very normal carbonate ooze. This carbonate ooze has been analyzed earlier in site 716, not so far away, by the working group of John Rhyme at the time being, with Lars Reuning. They looked at the diagenesis of the sediment in there, which is not interesting in this context. It's very interesting, but not in this context. And they did a very nice exercise. They looked at the calcareous zooplankton abundance of reticular fenestra, and they can show that you have these changes in abundance, which really nicely correlate with changes in the chlorine and TOC content. So what we do see here is the fossil expression of these nutrient influx pulses through time. This is a very nice study, but it has not been expanded to the entire succession, and it will be for sure interesting to expand this and to see how this thing varied through time. A nice work which is just in review. It's by Carlos Sarikian, who was the staff scientist of our IODP expedition. He's working on ostracods, and just to the left-hand side, a very nice plate, because the preservation of these ostracods is amazing. You would expect it in a carbonate ooze; they are encrusted and so on, but that's a very fantastic preservation. And he did a study for the last 2 million years, where he came up with several associations of those ostracods. And the interesting thing is, I'm running a little bit short of time, and so I shortened this a little bit. The interesting thing is that you see clear glacial, interglacial variations. He has these glacial faunas, which are characterized by robust elements which indicate that there is a highly oxygenated seafloor, that there are high current speeds sitting in there, whereas the interglacial faunas are indicative. They are infaunas. They are more indicative of sluggish conditions and nutrient rich conditions. And he directly links this to the monsoonal signal, which changes according to glacial and interglacial conditions. The organic content for sure can be traced throughout the succession by the gamma ray, because we notice that the total gamma ray, here the green curve in the downhole logs, is really a function of the uranium content here on the right-hand side. You see that thorium and potassium, they are just doing white noise, but they are not really influencing the total gamma ray curve. And we did an experiment, and we know that these layers rich in uranium are rich in organic content. So we can trace this back into time. So if we now come to the long-term evolution, what could we find? What could we find out? So we had all this business about the seismic lines showing all these changes in platform configuration. We can trace the productivity back using our gamma ray logs from different sites. We have these high productivity peaks in here. So I forgot to say the horizontal scale is the age scale from today to 25 million years back in here. So we have these organic rich deposits in here. So these are the subpropails in here. Then we have these more oxygenated conditions. And then together with the onset of this monsoonal circulation, you get higher productivity here in the waters of the inner sea. By using the manganese to calcium ratio, we can also show that together with the onset of this current-dominated system, we have an expansion of the oxygen minimum zone reaching the Maldives archipelago. And finally, first data on the dust flux here using the magnetic susceptibility. We can see that around 20 to 23 million years ago, the dust flux comes in the Maldives, and then it rose to a maximum and it went down. But these data are not reaching to the seafloor because these are logging data. We will now look at the dust flux in a different data set, so the dust record now. And the dust record in the Maldives, it's relatively easy to work on the dust record because the Maldives deposits are almost pure carbonate. So you see the carbonate values in here. So we have 80 to 95% of carbonate, and you just have to dissolve the carbonates, and you have the residual, and you have your lithogenic grain. The heterogeneous influx also can be measured by XRF data, and here a nice study by Mangeke et al. Published in 2020. They did a lot of XRF, of discrete XRF measurements. The topic of this study was to reconstruct the calcification degree of planktonic forms. For us, it's interesting to see that the heterogeneous influx in there, based on titanium aluminum ratios, began to increase around 12 million of years. So Teresa in Edinburgh looked at this heterogeneous flux for the last 2 million years, and she looked at the lithogenic grains. So here, just some SEM images. So the A, that's a dolomite, the dolomite crystal. So that's not important for us, but this B, C, and D, these are the quartz grain, the pitted quartz grains, which we can find in these residues. And you see these quartz grains are quite large in size. So what's the provenance of these grains? So Yao and co-author, Shengguan Yao and co-author just submitted a paper, a manuscript some weeks ago, looking at the neodymium isotope data from this area. Here just some published neodymium values of the Kenya Rift, Sahara, the tar sands in India, the Ganges-Brahmaputra River, and so on. And the blue, I painted this blue color in here. These are the neodymium values for the lithogenic grains in the Maldives, and you can see they are differentiated from 0 to 5, 5 to 7, and 7 to 12 million of years. And you see it's an absolutely mixed signal. This means that we have several sources contributing in there, and this really beautifully fits to the present day status. What you do see here is atmospheric data. These are flowback trajectories for a station, for a meteorological station located at the northern tip of the Maldives, and we see So that's a reconstruction for the 10th of March, the 14th of March, under dry conditions and wet conditions. And you see that sometimes particles come here from the Arabian Peninsula, from India, and at other times you have these particles coming more from the east. So a very nicely, a very nice reason to get this mixed provenance. Teresa also looked at discrete XRF measurements to translate this to the XRF scans of the core, and she came up, she did several tests because of water content and drying of the samples and different machines. But what is important is that we can really see that we have consistent data according to the different methods. So the amplitudes are varying, but you can very nicely trace the trends, and you can differentiate very nicely between dry and wet conditions. And so she produced the aridity record for the last 2 million of years, where she showed how the eccentricity and precession are really driving this lithogenic flux, and that we had these warm and seasonally wet conditions during the interglacials and colder and drier conditions during the glacials. We have marked changes around the mid-Pleistocene transition, and in green here, stage 22. This is the first relatively cold record we have based on our on our data. So the cold and arid record, and stage 31 in here is one of the latest wet record in the succession. So the last topic, that's work done by Sebastian Lindhorst here with us in Hamburg. He looked now at the grain size variations of this lithogenic grain. He came up with very exciting results. We could only do this for the last 4 million of years. We would have loved to go further down, but at a certain point, chert comes in the succession, and it's difficult to separate the chert from the lithogenic grain. So by measuring the amount of lithogenic grain in the fraction 8 to 63 micron, you can reconstruct the dust, or the dust flux, so the amount of dust in the system. So you can see that with the closure of the Indonesian Seaway, the dust amount rises. It keeps stable more or less to a certain degree, and then at the mid-Pleistocene transition, it goes up and fluctuates since then. By looking at the grain size of these, so that's the 90 percentile of the grain size 8 to 63 micron. By looking at the grain size, you can look at the wind speed. So higher wind speed means coarser grain size. So you see that here the grain size increases, it decreases a little bit. There's a little decrease in wind strength in the year. It goes a little bit up again at the mid-Pleistocene transition, but then from there on it fluctuates strongly. So here we also did some wavelet transform on this, and we see that the wind strength seems to follow orbital signals more in a better way, or more faithfully than the dust flux, which also has a certain signal in there, but it's not so clear as is for the wind strengths. Okay, so this was it, and a big thank you to all these fantastic people of the IODP expedition here. A photograph of the scientists, the technicians also made a lot, helped a lot, and we also had all these people, the shore-based people who did this huge amount of work, which I would like to thank. Okay, so I'm ready for questions.
Thank you very much, Christian. Fascinating talk with already published results and some exciting new things coming. And I'm sure this will come for years. There are lots of materials and lots of science to be done on those cores, and hopefully return back. It's fascinating how Maldives act as a trap, and what I was mostly interested in is how you weave the dynamics of the carbonate platform with the climate. That's something unexpected. Thank you again. I see we have already some questions from Peter Clift. If he typed it here, probably wants us to look at it. It's how much of the productivity is linked to the winter versus the summer monsoon? That's a good question. If you can differentiate between winter and summer.
Well, there seems to be so, and so I don't see the chat, but you asked me the question. So probably what we see at site 1467, the productivity seems to be higher during the summer monsoon time. So you have more organic matter in there, and you have more sluggish water. So that's the, let's say, the result we do have at the moment. But we have to go more into depth in this.
So productivity increased during the summer monsoon, yes. And that the currents during the summer monsoon, I see they are from
west to east.
West to east at the
Maldives. They are much stronger also, huh?
Yes, much stronger.
Thanks, Christian.
Questions? Please type them in the chat or ask them yourself. Unmute. If there are no questions, I have one. I was fascinated by that sapropel, and 35% were organic carbon.
Yes.
I didn't read the papers. I didn't read the papers from Swart at all. But is it possible to have that in open ocean?
Oh. It's there.
Is there any possibility that you have that platform almost closed?
Well, but you know, that's what we thought, because I saw that. I said, okay, that's a typical atoll which is totally disconnected, and you have stinking water mass in there and looking at all, but then you have this pelagic flora in there.
You have restricted connections, maybe. It looks to me exactly like the coccolith layers from the Black Sea with the sapropels. Yeah. Alternation.
So we would have expected to have other floral elements in there, but they're just open ocean.
Wow.
Yeah.
That's fascinating.
I think all N asked something.
Yes, please.
Hi, Christian. That was fascinating. Thank you very much. My question is regarding this transition at 13 million years. How abrupt is it? Is it really a relatively fast transition, or do you see a sort of gradual change at that time?
We don't. I mean, so we should differentiate between. I move. I don't know where this has been. So from the geometries in there, here, for example, it's a very abrupt change. You can put your hands in there. Yeah, it's a surface where you have this change. You may have a little bit, but it's difficult to say. So before the sequence boundary in this place, there is a little bit strange sedimentation going on, but it's not indicative of high currents. So the currents really come in there very abruptly. So now the question, the question is why is that?
Exactly, yeah.
Why is that? So I could imagine that maybe we have passed a threshold, you know, that we have a threshold situation. At some point, it just breaks through. But if you remember what I've shown you from this multi-beam imagery, we can see this abrupt change everywhere. Yeah, we never see a transition. It's always one system and then it goes to the other. But it's always in geology, especially if you're speaking of such deposits. So you never know how much is missing in time. Maybe 2,000, 3,000, 4,000 years are missing, but we would not notice that. But on geological time scale, with the time resolution we do have, with the resolution of the cores we have, it's an abrupt signal.
Thank you.
And is this upwelling signal, how do you link it to a global?
That's a good
versus the local, where
Oh, you
local factor would be the monsoon and global would be sea level.
For the upwelling? No, not so much.
No,
Not so much.
so the threshold would not be linked to anything
It's
global.
just the strength of the winds, isn't it?
Mhm. Any more questions? While we wait for questions, I would like to remind everybody that next week we will be on Schedule B, and we will have Christophe Collin talking about the Bay of Bengal. Tara would host. If there are no questions, I would like to thank you again. It was wonderful to hear news from 359 and see new results. And let's thank Christian for this, and see you everybody next week. Thank you, Christian.
Thanks a lot
Thank
also
you,
for organizing this fantastic thing. Really like it.
Bye-bye.
Stay
Bye.
safe.
Stay safe.